here's chapter 9. What are we going to do? We've already got the concept of sequence diagrams down, so we've been kind of toying a little bit with chapter 9 already. What we're going to really do is this part, okay? Because we've already done, this part, and this part with a homework problem, haven't we? We've got the concept of sequence diagrams down a little bit. We know how to go ahead and actually build them, to draw them out, and then actually build these network admittances. What we don't have is sort of this approach to do it generically, and I was kind of doing that with the lab number 6. You can take a look at that. So let's begin. Here's a simple system, right? So if you want some additional practice, positive sequence diagram, pretty simple. We come up through the generator. Oops, we don't do that. Sorry. We go through the generator. Now we have our source, right? This is bus 1. So we'll say this is 1, as I draw 2, 2. Actually, we won't draw a 3 over here. We'll just say that that's the same one as 2, because we don't have any line impedance, right? So, or do we have line impedance? Let me just look forward here. We do have a line impedance, so I do need to draw that. So here's bus 3, bus 4, and then that's it, right? So we're just going to blow right through the transformer. I don't even care how it's connected. This is bus 2. I have a line impedance. Bus 3. Bus 4. And then I have 2 separate generators connected. That's the positive sequence diagram pretty quickly, right? For negative sequence, get rid of those. For zero sequence, we have to go ahead and figure out what that value is. We know what this one is. We have to look at the transformer connection here. The line is going to be the line, so it doesn't change anything. We need that connection, and that connection. So let's actually, how do you calculate the size of that resistor? What does R equal? Anybody ever seen a resistor rated for 400 amps? Pardon? Not at the power system level. No, it's actually rated in amps. When you go buy a neutral grounding resistor, you tell them what the voltage is and what current you want. Hint, hint, wink, wink. If you know the voltage and the current, can't you solve for the resistor size? So how do you solve for R? Pardon? V over I. What's the value of V that I put? That's in per unit. I need it to be in ohms. So what is the actual voltage? Isn't it 20 kV divided by 400 amps? But be careful. What type of voltage is this? A three-phase line voltage. I actually want that to be a phase voltage. So to solve for the R value, you just solve for the phase voltage, 20 divided by square root of 3, divided by the current, and that gives you the amps. And the reason being is because if I have a generator here, and let's just look at one phase, if I want to limit the current through ground, this is 20 kV over the square root of 3. This is R. If I want this to be limited to 400 amps, doesn't that R have to be the only limiting device? The worst case scenario I'm going to see is if I have a dead short to ground on a single phase, I'm limiting that to 400 amps by specifying that resistor to be 20 kV divided by the square root of 3 divided by 400. That's how I actually specify it. Okay? So let's make myself a little more room here. So now I have my my zero sequence, I have my reference bus. This is 3 times that neutral impedance. I have my generator. Then I connect to bus 1. How does the transformer, how do I get through that transformer?
Dead end on that side.
It's dead-ended on this side. Up and through. Bus 2, right? because of the delta Y transformer. Then I go through the line impedance. Now I'm at bus 3. What happens at bus 3? It's Y grounded. So I connect over here, drop it to ground. I open circuit it. I have number 4. Then I have one generator. I'll do the top one first. This is 3ZN because of a solid ground there. The other one, I have the generator, but I just open circuit it, right? Because there's no current that flows through that Y because it's not connected to ground. So that is the positive and zero sequence diagrams for this transformer. Questions on that? Did I go too fast? I did. Where did I lose people? Bus 4? Well, let's look, right? So this is bus 4, we said. So if I look at this generator, I go into the generator. Here's the Y connection. Is zero sequence current allowed to flow through ground in this one? Yeah, because it's a solid connection to ground. How about this one? It's Y connected. Is there a path to ground? There is not. It is hanging open. So that does not provide a ground reference. It's not going to allow zero sequence current to flow.
So when you do your Y bus for that bus 4, would you still add that impedance in for the other?
Good question. So this one right here, do I add that impedance there into the Y bus? So if I'm building my Y bus 0, and I'm way down here at the 4, I'm going to have the 1 over 3ZN plus Z0. Do I add that impedance there? That impedance is the impedance of this generator here. Would I add that one in there? I get some heads nodding yes and some head nodding no.
I don't think so because it's not connected to ground.
Yeah, it's not connected, right? So when we did our Y bus for our three-phase systems, we have to have current flow flowing through them to actually have an impact on the impedance. Can any zero sequence ever flow through that element? No. So that's the only one. I don't even include this one, right? Because it's not even connected to bus 3. So the only one that's going to be and here's a key thing to highlight in your notes because you'll hear this term a lot if you work in the utility industry. The only thing that can be a ground source, which is a path, another way to say path or ground current, is this generator here. That's the only source for ground current on the entire system. If I have a ground here, there is no zero sequence current flowing up through that generator. None. Okay? So here are the diagrams, and if you want to check why I knew there was an impedance, right? There's the transformer. This is the actual value that you have. This is all done in per unit. And then if you want to check my results here, right, this should match up pretty closely. This is another good thing too. Remember how we talked about coordinating systems? Isn't the generator system here electrically isolated from the zero sequence perspective from the transmission system, which is electrically isolated from the next generator system? So in terms of coordination, I don't have to worry about coordinating those systems because the current doesn't actually transfer through. What becomes an issue is most of the time, the generator manufacturers, if they're generating, or the generator owners, they actually own these big generator transformers, these GSUs. So they actually have to protect their property, which means that they actually are concerned about that one. So the generator itself, it coordinates pretty much by default based on this transformer. The problem is if you have a ground fault over here and the utility has set their system with 67N elements, then this one right here, which is what the owner of the GSU is having to set, they have to coordinate. So that's one of the hiccups in the process in terms of getting all this stuff coordinated because the generator owners own the generator step-up transformers. That's very different than at your house. Do you own the pole mount outside your house? No, that's all owned by the utility. It's kind of a weird, interesting way to do things, right? But most of the time, the transformers are owned by the utility. If you're a generator company, you own the transformer. Any guesses as to why?
Because it's 4-year generator to step up.
Yeah, but what about the load? The load steps down to your house. Isn't that transformer there for your load? It's kind of a convenience thing. If you're a customer, like at your house, you have the equipment and the know-how and the ability to go put a pole-mounted transformer on there and run it all correctly and not get zapped. Ain't gonna happen, right? And the transformer that's outside your house, maybe 25 kVA, 15 kVA, you can go to Amera and they've got yards full of those for spare. They break all the time and then they can be replaced. This transformer here, a 350 MVA transformer, are you gonna go to Amera's parking lot and find a couple of those laying around? It ain't gonna happen. So from the perspective of what's the reality of it, and this is one of those ones where people have just said it makes common sense that the utility is not going to own this 350 MVA GSU transformer. It ain't happening. They do own big transformers out on the utility line, like phase shifters or auto transformers to step up transmission levels or step them down. They do own those, but they would never own a GSU unless, well, we're deregulated. But if the transmission system owns the generation, like in the Midwest and certain parts of the West, that would be a different story. But at least on the East Coast, generators always own their GSUs. So there's our diagram. Those are our Thevenin equivalents. How did we get those? That's what you're going to have to figure out. Question?
The Thevenin equivalent would be with reference to a certain bus.
Exactly. So you can actually hopefully very quickly figure out which bus I'm looking for. I tell you, right, is at the terminal of the machine, so it would be at bus 1. But there's another way to check to see what that impedance is pretty quickly. Okay? All right, are you ready to look at unbalanced fault, single line to ground fault? Any questions? Because all we've done is what we did with homework, right? We took our diagram and we figured out positive sequence diagram, or we took our single line and we figured out how to make a positive sequence diagram, a negative sequence diagram, and a zero sequence diagram. What was the next step? Build Y-bus for each of those diagrams, right? Once we have Y-bus for each of those diagrams, we can start to calculate fault currents as long as we know what the Thevenin equivalent voltages are at each of those buses. So, what's one way to get the Thevenin equivalent voltages at each bus? It's your friend and mine. It's an NRLF, Newton-Raphson load flow, right? So if you actually have PSSE or PSLF, you can actually do a Newton-Raphson load flow. Most of the time, though, you actually do what's called a current. It's basically V equals Y inverse times I. So if you know what some nominal loads are of the system and you have Y-bus, you can pretty quickly calculate just by using this equation to solve for your voltages, right? So I can't remember what that's called in Aspen, but that's an actual diagram that you can select. The other option that you can do is flat start. Set your voltage to 1.03 per unit or 1.04 per unit, which should be the worst case fault currents, and then go ahead and calculate from there. All the bus voltages are at 1.03, 1.04. There's no calculations that are done. Okay, so that's another way to do it. Those are the three options. 1, 2, 3. This is the best, but it's rarely done because most people in this room don't even know how to spell PSSE. I've seen it. I played with it a little bit, but I would consider myself before a novice in terms of its use. So more than likely, you will never be able to do a load flow for a real-world system unless you do something at an industrial system. This one is probably the most likely, as long as you have a decent system, and probably the closest to accurate without having to do a full-blown load flow. And then this one is less likely and fairly conservative. So this is very important. Make sure you know which one you're starting with. So if a customer says, hey, I want to calculate fault currents, you need to figure out, am I modeling it from a V equals Y inverse times I? Do I have enough information on the loads in my system? Or will I just use a flat start? Okay? This one is if you're using Aspen and you're modeling the transmission line. This one is more likely if you're doing power tools for Windows or ETAP or Easy Power or one of those programs where you don't really know what the loading is, so you're just going to be conservative. This is rare. Like I said, I've never done a load flow, a full-blown load flow of a transmission. I've done them on a couple distribution cases, but pretty rare.
But it's what PSSE uses.
Yes, PSSE can do it, but again, that's, you know, if you looked at the PSSE, which is probably at version 40 now, and if you could actually buy the books, there's probably 10,000 pages of material on how to use the software. I mean, it takes years to know how to use PSSE reasonably well. But PSSE does more than just load flow. It does transients. It does a bunch of other things. So PSLF you can learn pretty quickly, but most people that I know don't use it. So, all right, so let's look at a single line of ground fault. We have enough time. We're going to start with a phase A fault. And we're going to assume that the other currents, IC and IB, going to the fault are 0, right? There's no connection. So I'm going to go ahead and write that in a matrix as IA is an unknown, but IB and IC are going to be equal to 0, all right? And then I'm going to go ahead and calculate what my symmetrical components are, right? So this is the 0, right? Whoops. 0, positive, and negative sequence components. And if I just run it through my I symmetrical equals A inverse times I phase, and if this is an unknown value, I call it a question mark, but let's just call it IA at the fault. Well, I can see that IF is going to be 1 times the question mark, or 1/3, I should say. IF 0 is 1 again times the question mark, and IF negative is 1/3 times the question mark. Since these other two are 0, they don't have anything. So what that tells me is my positive, negative, and 0 sequence currents are all the same. They have the exact same value. And they're going to be 1/3. So if I was doing a circuit, right? Think about this from a circuit's perspective. If I had a circuit where I had a 0 sequence diagram here, and I have a positive sequence diagram here, how could I make sure the current flow in this one is the same as the current flow in the positive sequence diagram? What if I connected them in series? Wouldn't this current be the same as this current if I connect them in series? So what you should be thinking about is saying, hey, my sequence currents are all the same. If I connect my sequence diagrams, right, because I'm building positive, negative, and 0 sequence, and I have to figure out how to couple them together to actually solve for currents, if I take those individual decoupled networks and just at the fault location, put them together, and in this case, it looks like it's going to be a series connection, then what do you know? I actually can solve for that. Let's continue on. Let's look at the voltages now, because we also want to make sure that we're going to get our fault current voltage, our VA, at the fault, had better be equal to VA0 plus VA1 plus VA2, right? Because I want to sum those voltages together when I'm putting them in series. So let's take a look. Yes, that holds true. So I'm going to take my positive sequence diagram, and so I'll model this as my positive sequence diagram, which has a source and an impedance. This is V Thevenin. What is this impedance here? It's Z Thevenin at the positive sequence diagram. This current flow is positive sequence current. This voltage is positive sequence voltage. Then I'm going to connect that to the negative sequence. What does a negative sequence have? Just has Z Thevenin 2, right? And its current is in the same direction because it's the same magnitude, and its voltage is VA2. I do the same thing for 0 sequence with my Thevenin equivalent. And then if I have any fault over here, and that's how I connect my sequence diagrams together. I put all three of them in series, and I build this network. So this is plus to minus VA at the fault. So if I have some sort of impedance at the fault, my voltage is not going to be 0. But you can see Kirchhoff's current law says I sum these three voltages together to get my fault voltage, and my currents are all the same. So how do you solve for a single line to ground fault? We like a process, right? Step 1, build Y bus for positive, negative, and 0 sequence, right? Step 2, find V Thevenin. Step 3, draw sequence networks, right? So you're going to be putting your V Thevenin in series with your Z Thevenin 1. You're going to just put your Z Thevenin 2 and your Z Thevenin 3, Z Thevenin 0. Connect in series. Solve. So how do I solve for IA0? Which also equals IA1, which also equals IA2. How would you solve for those currents? Anybody? Isn't this just a series circuit with one voltage source? So that's going to be equal to V Thevenin divided by this impedance plus this impedance, Z Thevenin 2, plus the Z Thevenin 0, plus whatever fault impedance I have. Those are your three sequence currents. Now I know all three symmetrical components. How do I solve for VA1? I'm just using a KVL loop here. So it's V Thevenin minus IA1 times Z Thevenin 1. I do the same approach for VA2, but there's no Thevenin equivalent source. So it's just minus IA2 Z Thevenin 2. And VA0 is just equal to minus IA0 Z Thevenin 0. Once I have that, I've got the ability to solve for ABC, right? Because I know all those currents, I can solve for my phase currents. I can do the same thing for voltages. So that's how you solve based on the actual model of your system. You take a model of the system, you solve for your sequence networks, you solve for the Thevenin equivalent impedances, right? So this is going to give you, when you invert your Y bus to get Z bus, and remember the diagonals are those Thevenin equivalent impedances. So you take your diagonals, and these are the diagonals from Y bus, from Z bus. Then you just connect them in series, and then that's how you solve for fault currents. That's exactly how we used to do fault current analysis before all our systems became unbalanced.
Did you just say the diagonals are equal to the Thevenin?
That's how you pull out from the Z bus. That's how you get those. Yep. So for single line to ground fault for the system, we have our voltage source. This is the positive sequence Z Thevenin, the negative sequence Z Thevenin, and the 0 sequence Z Thevenin. And then I assumed that Z at the fault was equal to 0. So I take my voltage, one at an angle of 0, unloaded system, divide it by the three summed together. So if you look at this guy right here, that's because I have two of those, right? And then I just add them all up. You will notice I included the 3 ZF in here just to be complete. So if you have a non-zero ZF, you would go ahead and do that. And then this tells me what I have for a positive sequence current, which also has to equal negative and 0 sequence current. When I plug that in, here's the current you get for IF. You can check, but you'll see that IB and IC equal 0. So this is the actual current, magnitude and, real and reactive part, right, of the current. What is usually more helpful is to solve for the magnitude of current. I don't really care what the angle is. I really only care what the magnitude of the current is. Questions on how to do single line to ground faults? How about for Tuesday then, for Thursday, you add in what would be the single line to ground fault on your system? A real world system. So you're going to do 3-phase, do single line to ground. Doable? You may want to take a look at the Lab 6 stuff beforehand because it might show you how to do that. But I don't think it'll take too much effort to do that. We've got a couple more minutes. You want to try to cram in line-to-line faults or sayonara for the day? Who votes for stay? 2?
Line is the last one.
No, we have line-to-line and double line to ground. Who wants to say sayonara? All right, sayonara.